try to integrate that thingy. And your first reaction is, what is that? It's not sine to the fourth power. That we know how to integrate. This is sine, and then inside 4x quantity squared. I certainly don't know how to integrate this thing, do you? But why would you not do such a thing? See, in many cases, in applied math, you have to solve differential equations a lot. You know, good old differential equations that we've been training for. And then whatever you had is just not really relevant to real life situation whatsoever. They were just too simple, too easy. No real life is that simple. Most of them don't even have a solution. Well, see, solving differential equation depends depending on your integrity. Can you integrate certain things or not? You know what I'm saying? Because differential equation comes in form of derivatives. And something like this shows up all the time. Actually, not that easy, but remember my programming example? That does not have a general, well, there is technically a general solution, but that general solution comes in a form of integral. It's an integral of something. In most cases, you don't know how to integrate it. So let's say we have something ugly like this. In real life, it's a lot uglier than this, but let's just simulate real life with this easy example. Then, how are we supposed to solve this differential equation? One way is you convert this thingy inside to Taylor series. Thing about Taylor series is they are polynomials. Polynomials integrate very easily. Of course, the trade-off is you have infinitely many terms now. So that is the trade-off. You get it? So let's give this a shot, shall we? Okay, we'll microwave it. How do you like that? Yeah, I'm definitely microwaving this. So when we have sine of x, zoom in. Sine of x, do you remember what this was? After that quiz, you definitely do now, right? X minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the 7 over 7 factorial and dot dot dot, right? And after doing series of transformations, we still have to see that see what daylight savings does to human brain. What's the word I'm looking for? Pattern. That was so difficult. So I'm gonna replace x with 4x and square while I'm at it, which is what's inside the integral. Okay, I'm gonna start with a constant because, oh no, I have an integral, see, the factor of daylight savings. So first one, I have 4x squared minus that thingy, so I have 4x to the 6th over 3 factorial now. Say yes. And then 4x, thank you, to the 10th over 5 factorial minus 4x to the 14th over 7 factorial dot dot dot. How about that? Say yes. Now we integrate. So if we integrate this, sine 4x here, square dx. Now I'm going to start with the c, because I don't want to put that c at the end of the eternity, plus u, right? Okay, this is just 4x cubed over reverse chain rule 4 and times 3. How about that? That 3 from the integration and this 4 from the chain rule. U sub, if you will. Too much integrity? Okay, minus, here's 4x. This will be 7, so we'll have 7 here, right? And that 4 still has to be here. And then we had 5 factorial. Did I forget to put 3 factorial here? No, it's the first term. So we still have 3 factorial here. Good. First term did not have any denominator. So the next term plus now this term. So we have 4x to the 11th. So we should have over 11 here, but 4 here. And then we had 5 factorial here. Good. Minus 4x. And the next one is 15. So we'll have 4 times 15 times 7 factorial. Okay. We cannot get rid of c because that's just constant of integration, right? We need more initial value. So that's c plus, can we put the rest of them in sigma? What do you say? Starting with this term. Good. Alrighty. What do you want to start the index with? That's kind of tricky here. Before I say what we start the index with, what is the easiest one to write? It sure looks like that factorial thingy. Correct? This is 1 factorial. This is 3 factorial, 5 factorial. So that's the odd number factorial, isn't it? So why don't we start with that? So is it 2n plus 1 factorial? If you want to start n from 0. If you want to start it from 1, then 2n minus 1. You get it? Say yes.
Yeah.
Okay. Actually, I think I'm going to need a lot more space than this. Zoom in. Okay, 2n plus 1. You like starting it from 0? Okay, sure. And then, oh, here's an easy one. We need 4, because that 4 is there everywhere. And then, what about this thingy? This number that goes here. And also, that shows up at 4x. I need space for 4x and that number. How did we get that number? Let's see. We started like this, right? 3. And we doubled it. You know what I'm saying? So this was already 2n plus 1 kind of thing. We doubled it, so we have 4n plus 2. Do you see these odd numbers are 2n plus 1s? And now we doubled it, so it's 4n plus 2. And then we added 1 by integrating, right? That became this 6 became 7. So check this out, 4n plus 3. Do you agree? Let's check. So when it's 3, right? This is a second term, right? This is 0, first term, right? So n is equal to 1 here. So 4n plus, yeah, that's 7. N is equal to 2 here. So 4n, 8 plus 3, 11. Yep, that works. You get it? Think like programmers. And then, of course, we need alternating sign. If I start with n, my first term starts with positive. So how about that? Oh, I have to write the same thing here, 4n plus 3. Whew. Okay, so this is ugly trade-off, but at least we integrated it, right? And then how do we evaluate it? Well, we shove it into our program, table series program. You know what I'm saying? And then we just crank the numbers out and we calculate the error and how big is the error and stuff. But one thing we want to check is we want to find the interval of convergence. Yeah, let's do that. So for that,
isn't it the sum to infinity?
Huh?
Isn't it the sum to infinity?
Yeah, it will. But I'd like to do it anyway. Let's do a ratio test. Limit and approaching.
I think he's saying you forgot to write infinity at the top with a sigma sign.
Oh, that. That's totally because of daylight savings. Yeah, limit. Okay, absolute value. Oh my God, let's write that ugly thing. 4x for n plus 3 over 4 for n plus 3 and 2n plus 1 factorial. Okay, so numerator we would have 4x 4n plus 7a. Would that be too much? Okay. And then here's 4, and then 4n plus 7 here, and then 2n plus 3 factorial, right? Y'all follow?
Yeah.
Okay, let's try to simplify that fraction without losing our sanity. 4's cancel. Can I still do this in daylight savings, right? Okay, I think here is 4n plus 3 and 4n plus 7 to start off. And then 4x term. Wait, I still have one of the factorials left over, so let's just put it as 2n plus 3. Good. Well, this factorials differ by 2, so I need one more term, 2n plus 2, 8. Is that how you cancel those factorials? You see something like factorials that you thought was pretty hard last year, now looks so trivial. What did I tell you? And then the x term, right? We have 4x to the 4th power, eh? Say yes.
Yeah.
It's not too much algebra, right? Okay. Now let's take a limit. This approaches 1. What about this whole thing? 4x to the 4th power over something with an n in the denominator. What does that approach? What do you say?
0.
That's 0. Really? Well, as long as x is not equal to infinity, it's 0, right? I mean, you don't really care what x is, as long all you need to know is it's a finite number. You know what I'm saying? So that is equal to 0, which is definitely less than 1, right? For, let me just write for all x that is real number, which is not does not include infinity. So our interval of convergence, radius of convergence, which one do you want? In this case, they are about the same, but which one do you want me to write down? It's not that hard, you just pick one. I write both. Radius of convergence. If you write it this way, it's infinity. If you want to say interval of convergence, then you have to write it like this. But do you remember that ball on the number line? Yeah. It's in this case at origin, that thing is infinitely big to include all of the real number line. You get it? We want to write this integral as power series, and then our error needs to be less than 10 to the negative 7. What? So this is similar to what we did yesterday, correct? You can think of this upper bound as x up here. You know what I'm saying? I'll do that with red. And then we can make an integral function. You know what I'm saying? Okay, so let's do that. But are you worried about this error? Because we usually use Lagrange error. But if we microwave this, because I really don't want to do this the long way, 1 over 1 plus x to the 7th. God, that's horrible. We have to microwave it, but once we microwave it, then we lose, like, we can't do Lagrange error. You see the problem with that? Yeah, how are we going to square these two? I mean, technically, this is just a number because we don't have x here, right? So the whole thing is just a number. So we have to think of that as an x and then create power series, Taylor series, and then we substitute, we evaluate it from 0 to 7, we integrate, basically, that's the scheme. But error is a big problem. Well, when this happens in mathematics, it's just dive in and do it. And see, many times students would like to imagine the whole thing through to the end, and usually your imagination is not that good. It ain't gonna happen. Well, it doesn't happen to me, so it's not gonna happen to you either. So mathematicians, we think with our pencil, okay? So we'll see what happens. 1 over 1 minus x. We'll start there, right? Because we're building this thing microwave way. So 1 plus x squared plus x cubed plus ... is what that thing was. So we switch x to negative x. So we have 1 minus x plus x squared minus x cubed ... Good. Now we replace x with x to the 7th power. So we have 1 over 1 plus x to the 7th power, which will be 1 minus x to the 7 plus x to the 14th minus x to the 21 and ... So far, so good. Say yes.
Yep.
Now we integrate. So integral from 0 to 1/2, and we don't have to put x up here, it's just integral. We know how to integrate this. So 1 over 1 plus x7 dx is equal to, this becomes x minus x to the 8th over 8 plus x to the 15th over 15. Very good. Minus x to the 22nd over 22, and then ... I like to have a general term here. Okay, what is my general term? We're gonna need something like this, right? And then put, if we are starting, depending on whether we are starting from the positive or negative, but we'll adjust. Okay, and then we're going to need x to the, now how did we create this? First it was 1, and then we replaced it by x to the 7, so we have 7, right? This is 7n, and then plus 1a, so 7n plus 1, good, over 7n plus 1 is our thing. Now, only thing is, do you want to start this thing from the positive, well, right, 0. The way it's written, starting from 0 makes more sense now, doesn't it? This is a 0th term, so we have x to the 1st power. You get it? So we don't add 1 here with this, just negative 1 to the nth power. You get it? I mean, technically there's more ... here. It's like, it seems like, it looks like it's terminating series. This is just the general term. Good. Now we substitute. So if you substitute 0, they are all 0. So we just need to substitute 1/2. So what we have is 1/2 minus, I'm going to write 1/8 here, and then 1/2 to the 8th plus 1/15 and 1/2 to the 15th minus 1 over 22, and then 1/2 to the 22 and dot dot dot. Oh, this does look like what we did yesterday, kind of, doesn't it? So we can put it into sigma notation now. So whole thing with a sigma, and starting from 0 to infinity, you can put -1 over, it was 7n plus 1, right? And to the 1/2 to the 7n plus 1. Huh? That was nice. And we are not going to get exact sum, but we can put it into our p-series program and then crank it out. But my error, right? My error. Error is this. Your real 1 over 1 plus x to the 7 dx minus my p7, right? Real minus the approximation. Well, that's what we usually call R7, correct? These two mean the same thing. AP loves this format, so I keep giving it to you, but that really means remainder term. Wait a minute. Now we have to walk back in the memory lane. Do you see the error of this? What kind of error are we looking for? It's not Lagrange, because x disappeared now, right? But if x disappeared, what kind of series is it?
Alternating series.
This is alternating series. What was the alternating series error? It's less than or equal to?
The next term.
The
very next term, right? B and plus 1 term. Without the alternating sign. So let's write that. If you substitute n plus 1, then this is equal to 1 over 7n plus 8, eh? And then we have 1/2 to the 7n plus 8. Good. That needs to be less than or equal to 10 to the -7. So that tells you n should be greater than or equal to, there's no good way to do this other than just playing with a calculator. It just needs to be greater than or equal to 2. How about that? So shall we calculate the partial sum, P7? Okay, so therefore we just need n is equal, that's 3 terms, not 2. This means second order polynomial. So our integral that you wanted to evaluate is approximately equal to P sub 2, evaluated 1/2, and that is when n is equal to 0, you get 1/2 with a positive number, minus the next term. Is easier to just look at this term up there instead of sigma, 1/8 and 1/2 to the 8th power, and the next term plus 1/15, 1/2 to the 15th power, and that's it. And if you punch the calculator, somebody verify this, but what I had last year was this. Did I get that right? Let's look at number 20. My question to you is, first, do we need to know whether this is absolutely convergent or not? Or do they just care about convergence?
Just convergence or divergence?
Just convergence. Can you tell whether if this is not absolutely convergent by looking at it? Can we compare it to this thingy? Oh, better yet, this thingy, you see? If we do a limit comparison test, just like cross those out and you see they are about the same thing, correct? And this P is equal to 1/2. So this is not going to be absolutely convergent, even if we wanted to know, right? So you can actually tell these things by just comparing the leading terms easily. but we don't have to do it, so we'll just do it with the alternating series then, okay? Okay, so alternating series test, and you don't have to title the test. So first, we'll take a limit n approaching infinity of this thingy inside square root n plus 1 over n plus 1. Okay. Now, which way would you like to do this? Number one, either we can L'Hospitalize it, or we can divide everything by n, square root n. Which way? Let's just L'Hospitalize it, right? That seems to be easy, less headache than dividing everything by n.
Mr. Kim?
Yeah.
Like last year, there were those rules that she gave us. If the bottom degree is higher, we could just automatically write 0. Can we do that?
No, of course not. Are you kidding?
Okay.
But actually, there's this technique. Whenever you have this type of thing, last year, this is also what you learned. You can divide everything by n. So this becomes 1. This becomes 0. Divide whatever is the highest term in the denominator, okay? Divide this by n, then you have this, right? And then we take a limit, and then this dies, and this dies. Get it? So you get 0. That's one technique from pre-calculus. Now we have L'Hopital's rule, so we can actually take a derivative, and this becomes 1, and that becomes 1 over 2n, 1 over 2 square root n, so that becomes 0. I mean, whichever way you want to do it. Okay, we got a little more tools in our tool belt. Okay, either way, it becomes 0. Number 2. So now, do you want to do it with the, in the Dropbox note, I did it with a derivative. But then now I have to look back and say, why did I do that? Probably one of the students wanted to see it that way. Should we do it just a regular inequality way, this thingy?
Yeah.
Yeah, let's do it this way. I mean, derivative is a perfectly valid way of doing it. So this is true only if we have square root. Oh, maybe now I see why I did it that way. This is less than or equal to square root n plus 1 and n plus 1. Ooh. Well, we'll see, right? Multiply upward. So what we have is n root n plus 1 plus root n plus 1 and plus n plus 1, right? On the left hand side. And on the right hand side of n root n and plus 2 root n, and I have plus n and plus 2. Good. So let's cancel a few things that we can. N's cancel out. And this is a little more headache than I wanted. Let's just write it and take a look at it. Okay, I have that. Then I have plus root and plus 1 here. And then let's clean this up. So I have n root n plus 2 root n. And I have plus 1. Yeah, this is a little more difficult than I wanted. I regret not taking derivative now. Maybe that's why I did it with a derivative. Huh? Since n is starting at 1, it is starting at 1. So we can make our case somewhat that 2 is going to make a big difference. But this is headache, more headache than it's worth. You know what I'm saying? So yeah, let's scrap this idea and then go with the derivative. Okay, it's like in the middle of a test, it's a judgment call, and sometimes we get attached to our first idea and then we just keep going at it. But let's not do that. So we'll just take a derivative. Derivative of this nth term. And if we can show that this is always negative, then it's strictly decreasing. You know what I'm saying? But then this thing has quotient rule. Okay, let's see. Let's suck it up and do it. Derivative of this is 1/2 power. Okay, that thingy. Is that too much differentiability or? Okay. So that and minus, and then derivative of the denominator, which is just 1. So we have this. Why do I put parenthesis there? I don't need a parenthesis. So far so good? Okay, then I'm going to distribute this thingy. So I will have 1/2 square root n. Too much algebra? Plus 1/2 square root n in the denominator minus, I see why I put parentheses because I screwed up. I do need a parenthesis. It's like that, hey? Minus square root n minus 1 over n plus 1 squared. Still with me? Say yes.
Yeah.
Okay, then what do you have? Well, this and this is a like term, isn't it? So I would have 1/2 square root n minus 1/2 of square root n minus 1 over n plus 1 squared. Okay, let's see. N is greater than 1, isn't it? And do you see n is greater than 1, so this is less than half, correct? Do you see that? And then this is negative, square root is always positive. This is -1, so this term, all I have to show is that this term is less than this, isn't it? So do you see that this is equal to, this thing is less than 0 for all n greater than or equal to 1, since your thingy, this thingy, 1/2 square root n is less than 1. If this is true, then comparing this thingy with that thingy, maybe I should write, I'm not going to switch it. This is negative, this is always negative, so the whole thing is negative. You know what I'm saying? So this passes the alternating series test. So we can say the series is convergent. Good? Questions? Okay, we'll look at 23 then. Okay, 23, looks like this one we need to know whether it's absolutely convergent or not, right? Okay, so let's take out the alternating sign and consider this. And from 1 to infinity. Why is my sigma always so ugly? I need to practice, that's ugly too. I need to practice how to write sigma pretty. Better? Is your sigma prettier than mine?
No.
Okay. Oh, okay, so I feel better now. Okay, if you want going to compare this, we definitely want to compare it with the harmonic series 1/n, eh? Taking away that. And that's divergent. So if I just write this, Now that's a gap. Okay. 1 to infinity of 1 over n. Is that true? Because I have just taken away that 1. So inequality, direction holds. And then, of course, this is harmonic series, but we cannot just use that as a fact. So we have to do an integral test. Might as well just write limit from 1 to b and b approaching infinity, right? Did I have the lower limit, the indexing, starting index correctly? If the inequality is pointing to the left. Because that's something you have to think about all the time. Is that right? Or do I want to change one of them to 2? This is correct. Throw a few rectangles, then you will see. And then we have integral test. And this thing becomes, of course, ln. And we are sure and this will become infinity, eh? Okay, so what we have here is not absolutely convergent. Good. So now we do an alternating series test. Okay, number 1, the limit of the sequence inside that is dying out to 0, correct? Okay, actually I'm going to use different color for alternating series test. There, so I can use this space. Number 2, now this b n plus 1 has to be less than or equal to bn. Okay, that means here 2 plus n over n plus 1 quantity square needs to be less than or equal to 1 plus n over n squared. Eh? And then not to forget that if and only if sign. Okay, this one multiply. So I would have, let's write it this way, n cubed plus 2n squared. Eh? And that way, that is n plus 1 cubed, right? 1331, Pascal's triangle, binomial theorem. We can all do this, right? Too much algebra? I mean, at this level, you should know how to prove binomial theorem. So you should definitely know how to use it. Okay, simplify and cancel things from both sides, and cubes cancel. So what we have is 0 is less than or equal to, we have n squared plus 3n plus 1. And that's true for all n now, isn't it? Yeah, this is true. Good. Definitely greater than 1, but it's true for, just write it. It's my habit. But you don't need greater than 1. Oh, it's quadratic, so you definitely want to write greater than 1. N is assumed to be a whole number anyways, 0 and up, so you don't have to, but hey. Okay, so what we have here is conditional convergence, eh? Because something that is not absolutely convergent, but it's convergent anyway. You know what I'm saying? So this is conditional convergence. Conditionally convergent. Good. Okay. Now, then, do we have to do our error thingy? What does the instruction say?
It says give a bound for the truncation error after 99 terms.
Okay, good. So we just want to know what R sub 99 absolute value is, right? What was the alternating series error? It is the very term without the alternating sign, right? And that is, if you substitute 100, you get 101 over 100 squared. How about that? Good. Say yes.
Yep.
Okay, 25. Okay, another alternating series. So let's say, oh, we know it's gonna diverge, not absolutely convergent, right? How do we know? Well, let's see. Oh, they're starting it with 2, and just this thingy, and ln n, and we want to do an integral test. Do you know how to integrate this?
U sub.
U sub, of course, right? B approaching infinity. And we'll leave this, and then let's say u is equal to here. U is equal to ln x, eh? And then du is equal to 1 over x dx, isn't it? So do you see that this becomes 1 over u du? Do you see that?
Yeah.
Do you not see that? Okay. Now we have to change these guys or bring x back. Let's see if it's easy enough. So if we plug in 2 here, this becomes ln2. So it's not bad, right? ln2. So far, so good. And then if we plug in b, this is ln b. I skipped a line, but do you get it? Or should we bring x back and not deal with that ln b? Or is this good? Whichever way you want to see it is the way I will do it. Is this good?
Yeah.
Okay. You notice that I didn't put any direction here yet. But now I can see this is definitely divergent, isn't it? So this is limit b approaching infinity of ln u. Good. And from ln2 to ln b. So this thing becomes limit b approaching infinity of ln b minus ln2. Good. Which becomes infinity. So I definitely want to put it that way. That means I start this series from index 2. Good. Say yes.
Yeah.
So this is not absolutely convergent. Okay, then we perform alternating series test. You don't have to write the title. I'm just doing it for teaching purpose. Let's push these guys down. Okay, alternating series test number 1. Sequence inside, which is n ln n. So let's take a limit of n approaching infinity of 1 over n ln n. Oh, that's definitely 0, right?
Yep.
Okay, number 2. Bn plus 1 needs to be less than or equal to that. So I have 1 over n plus 1 ln n plus 1 here. And that needs to be less than 1 over n ln n. And that's true. I mean, you can feel it, right? n ln n is less than n plus 1 ln n plus 1. Oh, that's true for all n. In this case, greater than 2, but you don't have to write it. Okay, so our conclusion is the series is conditionally convergent. How about that? Good. Questions? Okay, let's do 30 now. Okay. Okay, shall we write this out? Maybe we can rewrite this, because at the moment, what do you deal with that cosine, right? So let's write this out. When n is equal to 1, what do you have if you put 1 here? Cosine pi is... this is when you're in recording, you're supposed to spit out again. Negative 1, thank you. So we have -1/1, right? Okay, when n is equal to 2. Oh, somebody tell me what cosine 2 pi is?
1.
1/2√2. Good. Wait a minute, instead of 2√2, should we put 2 to the 3/2 power? Yeah, that sounds like smarter decision. Okay, when n is equal to 3?
-1.
Right? Oh, so this mysterious series reveals itself. Let's rewrite it. So we can rewrite this as n starting from 1 to infinity of -1 to the nth power and n to the 3/2 power, eh? How about that, huh? Yeah. And it's going to converge because it's a p-series and p is equal to 3/2 more than 1. So it's going to be absolutely convergent. Do you feel it? So let's see if this thing is absolutely convergent. So I need to know if this is convergent. You know what I'm saying? Well, why don't I compare it with this integral then? Did I write n there? I meant x. Don't do that, it's annoying. Okay? That, of course, is limit b approaching infinity from 1 to b of x to the -3/2, right? And that is equal to limit b approaching infinity of, is that x to the -1/2 power? Therefore, -2. I'm going to take -2 out here. I regret that decision. I'm just going to take 2 out here and then write negative. You get it? You with me?
Yeah.
So 2 limit b approaching infinity and use plumbing professor as always. So substitute 1 first. So 1 minus substitute b. So it's 1/√b, eh? And take a limit and this term dies. So we have 2. You with me? Then this is convergence. So I want the inequality to point that way. Only question left is this index 1 or 2? Which should we start this with? Or you want me to draw those rectangles? This is 2. Y'all see this is 2, or does anybody want to see a few rectangles? Put your hand if you want to see those rectangles. Okay, good. So y'all got it. So this is absolutely convergent now, isn't it? Right? Because like conclusion from this, and you don't even have to write this line, but going back to my original series, 1/n3/2 is less than or equal to 2 plus the first term, which is 1, so it's less than 3. You know what I'm saying? So what we have is absolute convergence. which is, if it's absolutely convergent, do we need to proceed with alternating series test?
No.
Remember, there was even a theorem for students who are confused, because I've seen students proceeding to alternating series test and conclude the series is conditionally. Are you kidding? This is absolutely convergent. That means it's still convergent, all right? If a statement is true absolutely, it's true statement.